start the topic energy. So today's topic is energy. So under this energy, we are mainly focusing into kinetic energy, potential energy, and spring. Okay. There are a few forms of energy that we learn into this session. Now, what is energy? A body is said to possess energy if it has capacity to do work. So whenever the body has the capacity to do work, it has some kind of energy and work. Both are mutually converted. That means we can convert one form of energy to the other form. Okay. That means in this situation, let us say the car is at point A. Now we are lifting the car from point A to point B. So whenever I am trying to raise the car from point A to point B, that means the body should have some kind of energy. So that body has having the kinetic energy, which is initial at point A. Now once I am pulling the car from point A to point B, so you can clearly see the kinetic energy is reducing, and ultimately the potential energy, which was zero initially, it is the maximum value reached. Okay. So potential energy is gained and kinetic energy is reduced. That means what you can say that it is converted. That is, we can convert one form of energy to the other form. Similarly, when the same car is moving downward from B to point C, you can clearly see that the potential energy is also reducing, kinetic energy is increasing gradually. So, whenever we are starting this situation, that means some form of energy is converted to the other form. So, we are mainly concentrating on the energy which is moving the mechanical energy. Okay. So, what is the form of mechanical energy? Mechanical energy is the kinetic energy and potential. So, these two are the energies known as the mechanical energy. And whenever I am saying that there is a change in energy, that means I want to get the idea about the mechanical. Okay. So physically, first of all, I want to calculate what is the kinetic energy. Let us say there is a man whose mass is m and he is moving with a velocity v. Okay. So corresponding to that kinetic energy is the energy possessed by the moving part. If the particle is moving, then only the particle has the kinetic energy. And we all know this kinetic energy is equal to half m v square. Okay. So this is the kinetic energy value whenever the particle is moving. So this number says that the kinetic energy is basically equals to half m v square. Now v square number is always positive. Whether the particle is moving forward or backward, that doesn't matter. If I say the particle is moving in this direction, if I say this is the v positive number, if the particle is moving in the left hand direction, if I say v is negative direction. So yes, since it is a square number, it is always a positive number. So m and v square are always positive quantity, so kinetic energy is always positive. It can never be negative, but it can also be zero also. So if kinetic energy is zero, means the body is at rest. If kinetic energy is equal to zero, then that way I can consider the particle is at rest. It is not moving. Okay. Now, different forms of energy can be related to the kinetic energy. Let us say the water is flowing. So flowing water has some kind of kinetic energy. Okay. And now this kinetic energy, once it comes down, so at this point the high amount of kinetic energy is used to convert into some other form of mechanical energy. Mostly in case of turbine, we use the run the water mills, that is the turbine part, to get the again the electrical form of energy. Now moving here, wind turbine. So whenever the wind is moving, so wind has some kind of kinetic energy. So that kinetic energy is utilized to run the wind turbine. Okay. Similarly, the moving vehicle causes the kinetic energy. Similarly, once we place the hammer on the nail, so nail is moving downward, that means the moving hammer has the kinetic energy that is being transmitted to the nail itself. So whenever the bodies are moving, that means the energy is there, that energy is the kinetic. Okay. Now we relate between the momentum and the kinetic. Okay. So during the Newton's law of the motion, we know the momentum is a vector quantity that is written as the basically equals to m into v. Product of mass into velocity vector. But kinetic energy is a scalar quantity. So I want to relate the magnitude of the momentum with the energy. Let us say the part of the particle is there whose velocity is v. So corresponding to that, I can write p equals to m into v. And that is the I am writing only the magnitude. Similarly, the same particle, if it is moving, should have the kinetic energy k is equal to half m v square. Half m v square. Now from this p equals to m into v, I can write v equals to p by m. Okay, if I put it over here, so I am getting half m into v square means p square by 2m square. Okay. So ultimately, it gives P square by 2m. So kinetic energy is equals to P square by 2m, or I can write P equals to under 2mk. So momentum can be written as the root of 2m into kinetic energy. Okay. So this is the relation between the momentum and the kinetic energy, and this is scalar probability. So I am only taking the effect of magnitude of moment, not the direction. So particle moving left or right, depending on that, the vector will be changed. But if I say the magnitude of the momentum, it is always P equals to m. I can write that. And corresponding to that, what I am getting that P equals to under root of 2m into K. Okay. Now similarly, once I am getting P equals to under root 2m into K, so our equation is P equals to under root 2m into K. So now you want to plot the relation graph. Okay. So for that, on the y-axis, I am putting the kinetic energy, that is K number, and on the x-axis, I am putting P number. So if I square both sides, so what I am getting, that is 2m into K should be equal to P square, or K should be equal to 1 by 2m into P square. So that is, it is a parabolic relation. It is a parabolic relation. So kinetic energy is always a positive number. So it is always positive. So whatever is the value of P, either it will be positive or negative. So K is always positive. So if we start from this point when the momentum is 0, if P equals to 0, so kinetic energy is also 0. Now particle is at rest, that means kinetic energy is 0. So as we increase the P value, so kinetic energy is increased, so it will increase in a parabolic manner. And if I reduce the kinetic energy, if we reduce the potential momentum, then the kinetic energy is also increased. Okay. So if I, on this scale, this is the plus P number. For the other side of the graph, this is the minus P. So P can be positive or negative. P can be positive or negative. So what is the value of P? Corresponding to that, I am getting the positive value of kinetic energy, and that variation is basically parabolic variation. Yeah, this is a parabolic variation. So this is only the upper part of the y-axis, upper part of the x-axis, because this diagram is the positive part. So I cannot go beyond this number. So there is no part of the lower. So this is the relation that I have already derived, that the momentum is written as the under root of 2m into kinetic energy. Okay. A body cannot have any momentum without having kinetic. Okay. That means if I say k equals to 0, kinetic energy equals to 0, it implies P equals to 0. Or if I say P equals to 0, then kinetic energy is also 0. Okay. So for a given body, P is always root of proportional to root of kinetic. Or under root dk. dk is a kinetic energy notation I am using over here. So momentum is always inversely directly proportional to root of kinetic energy. Now this is the variation. So it is a constant parabola where, because m is a constant, so what I am getting, that E equals to P square by 2 m, this variation is there. That is nothing but a parabolic variation, and that number 1 upon 2m is the constant. So m is constant. So if m is varying, then the parabola will be changed. Okay, initially what I am saying, that m is constant. So mass of the particle is not going to be changed. If the mass of the particle is not going to be changed, then I can directly write that P kinetic energy equals to P square by 2m. Okay. This is always parabolic. Now come to the potential energy. Now one of the important factor about the potential energy is that the potential is only defined. It is only defined for conservative force. Okay. For conservative force. So I have already said what are the conservative forces that there, and for conservative forces only I can define the potential energy. Okay. Now what is the basic definition of potential energy? First of all, I have to understand. Okay. So let us say I am raising a ball. I am moving a body upward. So once I am moving a body upward, that means I am doing a certain kind of work against the gravity. Why? Because gravity on this particular body is acting downward in always acting downward. Now, in order to move the body upward, I have to apply a force in the upward direction. So this force that I am applying on the body is on the external force. Okay. And this force that is on the body itself, that is the gravitational force. Okay. And between of the, because the external force present over this situation, the particle is moving from point A to point B. Let us say this is the point A, and finally the particle is coming to point B. Okay. So this much of displacement takes place because of the external force. So if I want to calculate the work done by the gravity, so that means gravity, as you know, that this is a conservative. is the conservative force. Hmm. So now I want to calculate the what is the work done by the conservative force. Now here the conservative force is the gravity, so I want to calculate the work done by gravity. Hmm. What is that number? That number is for that situation, the particle moving upward. Let us say that displacement is, let us say, h. I am moving the particle from A to B and I am creating a displacement of h. Okay. So force is acting downward. Hmm. So here mg is acting downward and h is acting upward. So work done is minus mg. So work done by gravity in displacing the particle from A to B is equals to minus h. Okay. Now what it does? So once you increase the height and I am shifting the position of the particle from point A to B, I see that the work done by the gravity is negative. That means on this particle some amount of energy is being stored. Okay. So what is that form of energy? That is called the potential. Okay. So how we define the potentiality? Potentiality rather is a change in potentiality delta U. What is delta U? Delta U is called the change in potential. Change in potentiality. What is that number? That number is nothing but the negative of work done by the conservative. So this is the conservative force called WC. So negative of WC is how much? Plus mgh. Okay. So change in potentiality is defined as the negative of work done by the conservative force. And first to identify what is the conservative force over here acting there. So here only the gravity is acting as a conservative force. And because of that the work done is minus. Okay. And finally what I am getting that the change in potential. Change in potentiality is nothing but the negative of work done by the conservative. So already work done by conservative force is minus mg. So we put another negative sign before that. So ultimately I am getting plus mg. So plus mg is the work done or change in potential. So change in potential means what? UV minus A. Potential at A, B location minus potential at A location. Why B? Because B is the final position and A is the initial position. So what I am saying that UV minus UV number is greater than 0. Why? Because mgh is positive. That means potential in the system is increased. Okay. So anything, any work, if it is done against the conservative, here I am working is being done against the conservative. So why? Because the number is negative. Okay. So negative number suggests that work done against gravity. Work is done against gravity. If work is done against gravity or against any non-conservative, any conservative force, either the conservative force may be electric force, electrostatic force, or maybe spring force, or maybe magnetic force, as I have already mentioned. So if work is being done against that force, then always potential in the system will increase. Okay, that is the idea. So if work is being done against the conservative force, then the potentiality is going to be increased. Okay. Similarly, so a man is falling down. Okay, a man is falling down. That means whenever he is falling down, so for this situation, let us say the mass of the particle is m. So mg is acting downward and the displacement is downward. Nah. So h is also in the same direction. So can I say work done by gravity in this situation is positive? Why? Because mg into h. So work done by gravity is positive in this situation. That means what I can say that work is done in favor of gravity. Here it is in favor of gravity. In favor of conservative force or gravity. So if the work is being done in favor of gravity, that means now the potentiality is increased. In this situation, as I am moving from point A to point B, gradually moving downward, so potentiality of the particle is going to be decreased. Okay, so there are two concepts. One is if I do the work against the conservative force or against the gravity, then work is going to be, energy is going to be increased. That the potentiality is going to be increased. If I am doing the same work in favor of the gravity, then the potentiality is going to be reduced. Okay. Now let us say I want to calculate the potentiality for this two situation. Whenever the particle, so this part is fixed, and the particle which is initially at point A, if I release it, so particle will fall down. Yeah, it will fall down. So as the particle moving downward, so gradually it comes to point B. So throughout this process, mg is acting downward. Mg is acting downward. Okay. So mg is acting downward means what I can say, the work done by mg is basically positive. So work done by gravity is equals to mg into a, that is positive number, and that is the positive work being done on the particle itself. Okay, that means potentiality has to be. So what I can say that whenever the particle comes from A to point B, so potentiality point B is always less than potentiality point A, because B is the final point, A is the initial point. And in the entire situation, what I can say that delta U, that is a change in potentiality, is nothing but negative of work done by the gravity, or negative of work done by the conservative force. So negative of work done is minus mgh, because work done by gravity is mgh. So negative of that number is minus mgh is there. So delta is what? Delta is basically final minus initial, UV minus UV. So clearly it is been observed that UV minus UV is minus mgh. That is negative. Okay. That is what you can say, UV is always going to be less than UV. Okay. So whenever the potentiality has to be calculated, the potentiality, you saw that potentiality may increase or may decrease. May increase or may decrease. So when you throw a ball upward with an initial velocity, it raises to a certain height. Okay. If I throw a ball with a velocity u, ultimately it goes to a particular point once the velocity becomes zero. Now, final velocity becomes zero. After that, the particle comes. So once the particle is coming to a momentarily at rest, so at this point, can I say kinetic energy of the particle becomes zero? So initially, what I am saying that whenever I am throwing the ball, so what is the kinetic energy? Kinetic energy is equals to half m into u square. Okay. At the initial point, let us say point A. And at the final point at point B, the kinetic energy comes zero. So throughout the movement of the particle from point A to B, the kinetic energy is reduced. Now, once the kinetic energy is being reduced, that means if one energy is reducing or decreasing, so I have to say that some other form is going to be increased. What is that form? The potential energy. So in the movement of particle from point A to B, what I say that from A to B, once I'm moving, the kinetic energy is going to decrease. Okay. And similarly, alternately, potential energy has to be increased. Why? Because the condition is that in this situation, again the work is being done by the track. Okay. If I throw the ball, so mg is acting downward. Okay. So work done by gravity or work done by conservative force can be written as equals to minus mg then. Okay. So delta is the change in potentiality, that is equals to minus of WC, that should be equal to plus mg. Okay. That means it is a positive number. So that means potentiality has to be increased. Okay. Indirectly, what you can say that if one energy is going to reduce, another energy has to be increased. So that the total mechanical energy is even constant. At any instant of time, if I say that total mechanical energy has to be constant. Okay. All the initial kinetic energy gets converted to potential energy at the maximum. So once I throw the ball from point A, so initially only the kinetic energy is there at point. Once I throw the ball at this point, all the kinetic energy becomes zero. Only the potential energy is there. It is not equal to zero. Okay. Initially at point A, I can assume that potential energy is equal to zero. Why? Because potential energy is not safe. Why? Because we are not calculating the potential. What I am calculating is the difference of potential with delta U number. Whenever I am calculating delta U basically UV minus UV. Okay. That number is always constant, that is plus. Okay. So I can declare that U at point A is 0. If I am saying that UVA is 0, then I can say UV equals to MGH. Okay. If I say UA is not equals to, let us say I am saying UA equals to, let us say MGH. Okay, UA equals to MGH. So UV becomes how much? 2 MGH. Okay, 2 MGH. That means every time you have to take care about the value of U at initial position A. So once I know the UA value, then correspondingly I can calculate the value of UV such that the difference of potential is always constant. So what I am trying to emphasize over here is that whenever the particle is moving, so throughout the situation, let us say the particle initially at point A, so as it moves down to point B, the kinetic energy is increased. Okay, that means some other form, there is a potential energy. Okay, So in the movement of particle from A to B, potential energy is reduced, kinetic energy is increased. Now in the other part, when the particle moving from B to C, what I can say, the kinetic energy is being decreased and potential energy is being increased. So if one energy is decreasing, another energy has to be increased. So potential energy is the energy associated with the relative position of two or more interactive particles. So between the interaction of the two particles, the potential energy depends. Okay. So potential energy in terms of conservative, because I have already said that the potential energy is only defined for the conservative forces. So delta U becomes minus of WC. Every time be careful about this negative sign. Why? Because in the definition, changing potential energy is always negative of work done by the conservative. Now, once I am saying conservative force, so let us say there is a particle. I have to raise the particle from point A to point B. Okay, from point A to point B, I have to raise the particle. That means the conservative force mg is acting downward, and in order to move the particle, I have to apply the external force. Okay, external force. So external force is always, so this force is the conservative force. Okay, this force is the conservative force. So external force work done is nothing but the negative of conservative force work done. So I can also write as plus of work done by the external. Okay. So negative of work done by the conservative force, or I can write work done, positive work done by the external force. Why? Because in this situation, the work is being done external force in order to move the particle by you. So what is the work done by external? External force will be equals to mg into h. Why? Because I am applying the same external force as that of the conservative force. So that particle will not gain any kind of acceleration. Okay. So it will move with constant speed. So that means I am applying a force which is almost equals to the conservative force, so that the particle can be raised. Once I am moving the particle very slowly, that means what I am ensuring that only the potential is stored at point B. Okay. So this is the two way to define the work done by the conservative force, or in the other word, I can define the changing potential. Okay. So mathematically, I am writing this equation. Or if I use the expression for the work done, so expression for the work done is minus of F dot dr. What is that F? That F must be the conservative. Okay. So mathematically, I can write is that integration of conservative force dot dr vector between A to B. That is giving the value of UB minus UA. So starting potential is known as the UA, that is the initial potential. At point A, I am defining the potential at point A. Okay. So corresponding to that point A, I am getting the value of UV. Corresponding to the value of UA, let us say I am giving UA value is equals to 10. And corresponding to that, let us say I am getting UV value as 40. So what is the UV minus UA number? That is 30. So delta U basically 30. So keeping the same value of 30, if I define the UA is equals to 0, let us say in the other situation I am taking UA equals to 0, then UV becomes 30. UV becomes 30 such that the difference of potential is always 30. So I have to take this UA number. Okay. So UA is called the reference potential. Reference value. Reference value. Now this reference value is always taken to for the gravitational law. Since I am doing the gravitational potential energy. Why? Because I am doing the work done calculation for the conservative force, which is the gravity. So for that, what I am saying that UA number you have to take it as 0 for the ground. Okay. Whenever the particle is on the ground itself, so at that ground I am taking the reference value of the potential energy as 0 number. So I can take any other number. There is no issue, but it is easier to take the 0 number at the reference value. If I move upward, then the UV is positive. Okay. So from the ground, if I move upward, if I am moving upward, then the UV will increase. Potential will increase. If I move downward, then the potential will decrease. And if you remain on the same point, that means on this ground, the potential is no change. There is no change in potential. So we can understand that the change in potential is basically mg number. So depending on that, how much amount of change is there, so that change is either positive or negative. Depending on that, from the reference point, what direction I am moving, direction I am moving. Now come to the spring potential. Why? Because it is another kind of conservative force. So for the spring force, I know that the spring force is basically the kx type of force. That is the kind of conservative force also. Okay. So since it is a conservative force, so I have to define the potentiality for this system also, for this situation. Let us say there is a spring block system. Now once I am moving the spring, that means initially this is the natural length, this is the natural length. Now a block is hitting the spring. So block is hitting means the block has the kinetic energy. Once the block is hitting the spring, that means spring will be now complex. So you can see that the kinetic energy of the block is converted to the potential energy of the spring. Okay. And ultimately what happens once the kinetic energy becomes zero, now the spring is elongated and pulls the block together. So now in the second part, the potential energy of the spring is used to convert the kinetic energy to get back the kinetic energy same. Okay, that means again I am getting the idea that the one form of energy is converted to the another. So block has the kinetic energy. Now once the block is colliding with the spring, so kinetic energy is converted to the potential energy. Kinetic energy is converted to the potential energy. But depending on that, similarly, the potential energy is again converted to the kinetic energy. That means it is converting to one point to the other. So now I want to calculate the expression of the spring potential. Let us say the spring is initially in the natural length position. Now once I displace the spring by a distance of, let us say, x, I am stretching the spring by a distance of a. So I know the spring force acting on this block is on the opposite direction of the elongation. So here the spring force is acting as a kx, the spring force. Now if you displace it further by dx distance. Okay. So from this position I am displacing further by dx distance. So now I want to calculate the work done by the conservative force. Now here the work done is by the spring force. Okay. So that should be equal to how much? Minus kx dot dx. Okay. Minus kx dot dx. So now what is the angle? Angle is again 180 degree. So ultimately what you write? So not minus kx. So simply write kx dot dx and automatically you put the value as 150 degree. So in this situation, the angle between the force and the displacement is 180 degree. At the angle is 180 degree. So the small work done in moving the spring from point A to point B by s dx distance, let us say dw. So dw is a small work done. So it is how much? That is equals to kx into dx. But since cos of 180 is minus kx. Okay. So let us say I want to calculate the total of work done. So if the part is bringing from, let us say, at x1 position to x2 position, I want to change the position from x1 to x2. So what is the work done? So integration of this from x1 to x2, x1 to x2. So that W net or the spring force work, that should be equals to minus k x2 square minus x1 square by 2. Okay, we put the limit, so it got the value of minus k times x2 square minus x1 square by 2. Okay. Now, this is the work done by the spring force. So negative of that will be the change in potentiality. So initially, what I am saying that the initially is the, let us say, the point, initial point, x1 location, and at the final point it is the final position. So delta u and the change in potentiality, that is equals to ux minus uy, that should be equals to minus of ws. Minus of ws. So minus of ws is what? So plus k into x2 square minus x1 square by 2. Okay. So that means what I am getting, u final minus u initial should be equals to k times x2 square by 2 minus k times x1 square by 2. Now if I closely look into this equation, so if I say initial position is our natural length. If I say if initial position belongs to our natural length. So at natural length, can I say x1 number is equal to 0, no elongation of the spring? So if x1 is not equals to 0, so if I relate this equation in this manner, so u final belongs to what? This number. And u initial belongs to this number. So if I say x1 equals to 0, that means initial potential energy becomes 0. So finally what I can write, spring potential energy should be equals to u, that is equals to half into k into x square. What is x? X is the total elongation. Starting from the natural length. Yeah, so if I elongate the spring from x equals to 0 to x, then the potential energy stored inside the spring is equal to half x square. Now again, if I look this number, So what I can understand that U number is always going to be positive. Why? Because it is half k x square. U can never be negative. So spring potential energy can be also written in the form that U final is equal to this equation. Whatever you got, that U final minus U initial equals to that number. Now, so U final is equals to U initial plus this number. So in most of the situation, if I take this U initial is equal to 0 at natural length, so that means initially the string is at natural length, so that means at x equals to x initial is also 0. It implies x initial is also 0. If I put x initial 0, Ey 0, so ultimately what I am getting the U, that is the spring potential is called basically half k into x final square or simply x square. This is the expression of the potentiality of the spring. This is also derived from the conservative force. That's why this is the second potentiality, that is the E. Again, this is variation is parabolic. Again, the variation is parabolic. So either I can elongate the spring or I can shorten the spring. So in this direction, x is positive. That means I am doing the elongation. In the other direction, x is negative. That means I am compressing the spring. So whether I am doing the elongation or compression of the spring, the potential energy of the spring is always going to be positive. Half x square. So since x square number is always positive, so half x square, that number is always positive, so E is always positive. You can never be negative. And from this equation, so since I am saying this is the vertex of the parabola, at this point x equals to 0, then the spring is in the natural length position. So corresponding to the value u equals to 0 also. Okay. So this is called the ideal spring situation. Why ideal spring? Because in the entire spring I am neglecting the mass of the spring. It is being massless. So that means it is behaving as a perfect ideal spring. So it is a parabolic function. The variation is parabolic. So similarly, I can define the gravitational potential energy. Similarly, I define the spring potential. So gravitational potential energy is basically the work done by the conservative force, and negative of that is the potential. Now I can further redefine it. So work done by the conservative force, and I write it as the force, conservative force into dx number. Okay. So dot product of force and dx, fc dot dx. That should be equals to minus a delta minus d. So correspondingly, I can define another equation, that is fc, that is equals to minus of du dx. Okay. So conservative force can also be known to be as the minus of du dx. Okay. Now u is a scalar equation. U is scalar. U is scalar. And f is a vector quantity. Now how to relate this? So for that you have to put the vector notation. Okay. So if I am saying that u is a single scalar variable, so if u is the function of x only, if u is the function of x only, then simply write conservative force f should be equals to minus of du dx multiplied by I. Okay. So if u is the function of x and y, then I have to use the partial differential operator. So partial differential operator means now I have to write f equals to minus of del u del x with I minus of del u del y with j. And if u is the function of x, y, j, so I have to use the I, j, k notation. Okay. So depending on the u number given, so u is what? U is called the potential function. U is called the potential function. If the potential function is scalar, so I have to write the corresponding vector equation. So for that, you have to rewrite the equation. So this is the final form. So for a 3D vector, that means whenever the three-dimensional force system is given, so for that f should be equals to minus of this. So del is the partial differential operator. So depending on the variable, I have to use the partial derivative. Let us say I am saying u number is given as this equation. I want to calculate. So since it is clearly seen that the u has three functions, x, y, and j. So I should write the f vector as minus of del u del x into I minus of del u del y into j minus of del u del z into k. Now del u del x, once I differentiate it with respect to a, so I have to assume that y and z are constant. So I am getting only minus 2x I. Similarly, once I am differentiating with respect to y, take x and z to be constant. So only getting 2 number. So minus 2j. Similarly, with respect to z, I am getting 3 number. So minus 3k. So that is the expression for the f vector. Okay. So from this expression, it is quite clear that the force is a 3D force. Why? Because there are three different variables and inputs. Okay, depending on the nature of the scalar function given to you, you have to identify what is the vector form. Similarly, so this is the first step of the situation where if u is known, in this situation u is known, from the known value of u I am calculating the force. Okay. The second part of the problem is that if f is known, second part of the problem if is known, so I have to use the integration format. So in this situation I am saying that f is known. Now we want to calculate the u number. So for that you know that f equals to minus of du dr. Right, in terms of r. Okay, r is the displacement vector that I have to use depending on the nature of the force. So ultimately what you write that du should be equals to minus of f dr, f dot dr. Now integration of this will give integration. So if I integrate it, so finally answer is u final minus u initial should be equals to minus of f dot dr. Now depending on the f value given, so since f is known, I have to do the integration. So now the right hand side of the integration is known. So finally what I can write u final should be equals to u initial minus integration of f dot. Okay. So from this equation you can calculate either the uf minus uy number or I can calculate the delta u number. Okay. So both way you are correct to calculate the u. So ultimately you have to calculate the final potential. So for that you should given the value of initial. Now this is the equation where u at point 1, 1 10 is given. That is, this is the u initial. You are asked to calculate the u final now. Okay. So what is the equation that you should do? That u final should be equal to uy minus integration f dot dr. Okay, this is the equation that I have to use. Now here the equation a vector is given as x square I plus yj. That means in this equation I have to use the dr equation as, so in this equation dr should be how much? Dr vector should be equals to dxi plus dy. Why? Because f is a 2D vector. That means I have to assume the dr as 2D vector also. Okay. So f dot dr becomes how much? If I want to calculate the f vector dot dr vector integration of this, that vector will be x square dx plus y dy integration. So for that you have to calculate the limit. So initially x number is at point 1 is 1, then finally it changes to 2. So put the limit from 1 to 2. For the y, it is from 1 to 3. So it gives x cube by 3. Limit is from 1 to 2. Plus y square by 2. Limit is from 1 to 3. So 2 cube means 8 minus 1 by 3. First number. Plus 3 square means 9 minus 1 square means 1 by 2. So this part is 8 by 2 means 4. This part is 7 by 3. 7 by 3 plus. So 12 plus 7 is 19. 19 by 3. Okay. So integration result is 19 by 3. So finally what you can do, you can put the value. So uf I have to calculate. Uf should be equal to how much? Uy. Uy is how much? 10 minus of integration result. So minus 19 by 3. Then is 30 minus 19 by 3 means 11 by 3. So 11 by 3 is the final potential. So this is the final answer. Uf is equal to 11 by 3. Provided u initial is given. Okay. So this is the second format of the problem where I have to calculate the potential energy from the equation of F. So if I have to calculate the U from F, so I have to do the integration. If I want to calculate the F from U, I have to go for the differential. Okay. So now you have to relate the potential energy. So far you know the potential is a function, U is one function, so there must be some kind of variation of this type. So let us say there is a potential energy variation versus x. X is what? X is the position. Okay. So there are some certain point where I can find that the slope becomes 0. No. So at point B and at point C, what I can understand that the slope is becoming 0. Okay. The slope is becoming 0. Here at point A, the slope is negative. At point D, the slope is positive. So at defined point, the slope is changing because the variation is not linear. So what is the slope indication? So you know that A equals to minus of du dx. So what is du dx? Du dx is nothing but the slope. So negative of the slope defines the force. Okay. So that means at point A, what you can say slope is negative. Nah. So negative of the slope, if the force, so force become positive. So force become positive means at point A, the force is positive, means in this direction. Similarly, at point B, so slope is positive. Slope is positive. But positive or negative is negative. So at point B, the force is in this direction. So by seeing the potentiality variation, I can identify what is the direction of the force first of all. And there are certain points where the slope becomes 0. At point B and C, slope becomes 0. If slope becomes 0, so that means at this point, I can say that force is acting also 0. Okay. So force at point B is 0. Force at point C equals to 0. Okay. So from the diagram, I can conclude what are the direction of forces as well as whether the force is 0 or not. Okay. Let us say first situation is that slope is positive. Slope is positive means let us say you identify the point B. You identify the point B, you had the slope is positive. Now slope is positive means what I can say the force is negative. Force is negative. So du dx positive means slope positive means force become negative. So force become negative means what? Force become negative means because the attractive type. If the force is negative, then the force is not the attractive. Hmm. I'm giving some example. Let us say you are displacing the mass from the natural by distance of x. By distance of x. Now at this position, if I draw the potentiality variation, so this is the potentiality variation. So this is the x location. This is the x location. At this point, I know that slope is how much? Slope is positive. So this is the point A. The slope at NA point is positive. The slope is positive. So once you release the mass, then the mass is automatically coming towards the natural. Why? Because the spring is pulling it. So that means this mass is observing a force which is attractive in nature. Okay. Why? Because the slope is positive, the force at this point is negative. So this is the force on point A. So this type of force is known as the attractive. Similarly, if I release a mass from a certain height, so again mg is acting downward. Again mg is acting downward. So I observe that the particle is moving toward the earth surface. That means earth is being pulled by the block or block is being pulled by the earth. So again this force is acting on the particle is basically a negative type of force, is the attractive type of force. Okay. So in all of the situation, whenever I got the hint that the slope is positive, that is what I can say. Slope is positive means the force is attractive. Okay. So opposite to this, the repulsive force. Opposite to this is the repulsive force. That means there are certain points on the diagram where the slope is negative. So at a point, let us say I am doing the calculation of the point A. Let us say point A, the slope is negative. Aim at point A is negative. If slope is negative, so negative of that number become positive. If now the force is positive, so at point A, force is positive in this direction. Force is positive. If the body is feeling a positive nature of force, then the force is known as repulsive. Okay. So repulsive nature. So in this situation, throughout the situation A to B, the particle is feeling a repulsive type of force. Repulsive type of force. And third is zero force. Zero force means at that particular situation, the du dx number should be equal to 0. That is slope is 0. Slope 0 means indirectly what you can say f is also 0. Okay. Now if I say the force acting on the particle is 0, that means particle must be in equilibrium. Okay. So why? Because we know that for equilibrium to happen, the particle net force must be equal to 0. So if I want to calculate the net force on the particle, and if I see if the particle is at point C or at point B location, if the potentiality variation is that I am observing the particle at point C or at point B. At both of these 2 points, I can say the slope is 0, that is net force 0. Okay. So if net force acting on a particle is 0, it is said to be in equilibrium. So particle is achieving the equilibrium at point B or at point C. So this is the most important condition for the equilibrium. Okay. So dudx should be pursued with the basic concept or the basic information that has to be satisfied for any type of equilibrium. But what is equilibrium? Equilibrium means, in simple word, net force on the party should be. But there are different types of equilibrium. So there are mainly three types of equilibrium of possible. Three types of equilibrium of possible. But for all those equilibrium, the basic case is that F should be equal to 0. Net force is equal to 0. Let us understand this situation. So, if I displace this bottle from its vertical plane in this direction, if I tilt it slightly, then after some point of time, it oscillates and ultimately comes to again equilibrium position. Initially, it is the equilibrium position. Vertical line is the equilibrium position. If I displace the bottle slightly and then release it, so what I observe that bottle is moving to and fro, then ultimately it is coming back to the same position. If that is happening, that is called stability. Okay. Now, on the other hand, if I displace it, then it will displace permanent. It will never come back to the original position. Okay, slightly tilt it, but it is not able to come back to its initial position. In that situation, is an unstable situation. And another equation is the neutral equation. I am displacing the particle, but I cannot understand what is the exact position of the particle. Why? Because if I take a snap, if I see the particles over here, on the other time the particle is over there, but there is no change of picture or no change in quality of the position of the particle between these two. The particle is always on the floor. Always on the floor. I cannot say the particle is falling down or moving upward, moving or not like that. Okay. It is always keeping the same position. So I am saying that this equilibrium is neutral. Okay. So possible equilibrium is three types of equilibrium: either stable equilibrium or unstable equilibrium or neutral. These are the three cases of the equilibrium. But if I study the U versus X diagram, U versus X diagram for this three situation, so at this position, the slope is 0. Okay. At this position, the slope is 0. At this position, again the slope is 0. So for each of the three diagram, U versus X diagram, slope is 0 everywhere. The slope 0 means the net force is 0. And net force is 0 means the particle is in equilibrium. That is correct. Now once I displace the particle, let us say I am moving back to this position. So at this position, if X is positive, so I can say clearly the slope at this location is positive. Here the slope is positive. So particle on that point X, feel the force in this direction, attractive force. Similarly, if I go toward this position, the slope is negative, so force becomes positive, so force is in this direction. So every time, if I try to displace the particle from this position, that is called the mean position. That is called the mean position. If I slightly disturb the particle from the mean position, the particle is feeling a kind of attractive. And because of that, it again comes back to the mean position. But in that situation, in that second situation, unstable situation, if I move to this position, here the slope is negative. So negative means force is positive. The heavy one. Here the slope is positive. So force is negative. So in both the situations, if I displace the particle slightly from left to right, either towards left or towards right, the force is repulsive image. So repulsive force gives the unstable equilibrium and attractive force gives the stable equilibrium. Whenever the force is attractive type, then it will always giving a stable kind of equilibrium. That means the particle will come back to the initial position. Now in the third situation, whenever I am talking about the neutral equilibrium, so again the slope is 0 everywhere. So whether the particle is at this location or this location or this location, at any instant, I can clearly say the slope is always 0. It is very perfectly straight line, but the position is not changing. I cannot identify what is the new position. Okay, that's why we call the neutral equilibrium. Okay, so these are the three kind of equilibrium based on the stability. So first one we discuss about the stability. So stable equilibrium means that if I consider a marble placed at the bottom of a spherical bowl, if I displace the marble from in this direction, so ultimately the particle will move to and fro movement up and down, and ultimately will come back to its position. Okay, so that means it is the kind of equilibrium which is called the stability. So for stable equilibrium, the first and foremost condition that du dx is, that is true. Du dx is 0. And potentiality has to be minimum. Why? Because in this situation, the diagram of the potentiality versus X diagram is like this. Q versus X diagram. So this is the minimum potential. Okay, this is the minimum value of potentiality. So you have to minimize this function. The second derivative must be positive. Second derivative must be positive. So these are the two conditions which will satisfy the stability criteria. So whether the particle achieves the stability equilibrium or not, that defines by these two criteria. Similarly, for the unstable situation, it should be maximal. That means now the particle should lie at the top of the vertex in the maximum position. Means the second derivative must be negative. So first condition remains same, second derivative is negative. Okay. So if the marble is placed on top of the ball, so if I displace the marble, it will never come back to the initial position. It will go on in this direction or in that direction. It will never come. Okay. That means it is a kind of equilibrium which is unstable in nature. And for the neutral, both are to be. U will be equal to 0 and second derivative will also equal to 0. So that means a marble placed on horizontal smooth table, if I displace this particle, I cannot identify what is the new position. Both the positions seem to be same for me. Okay. Both the position seems to be same for me. That means this type of equation or this type of equilibrium is known as the neutral equilibrium. Okay, neutral equilibrium. And in neutral equilibrium, potentiality is always constant. Always constant because it becomes a straight line top. Okay. So based on these three concepts, we define the equilibrium and let us check for equilibrium. It has given that the value of u is given as 8x minus x square. So first step is to calculate the differentiation du dx. Okay, because du dx has to be 0 for equilibrium. So what is du dx? That is 8 minus 2x. So that means if it is equals to 0, so x equals to 4. So at 4, the equilibrium exists. Now I have to check whether this equilibrium maximum minimum. That means further I have to check the du dx square value. Du dx square. So once I do the du dx square, it gives minus. That is negative. So that means it does not depend on the x value. So I am getting negative value of du dx square. That means it equals stable equilibrium. This is a kind of equilibrium stable. And what is the location? Location is x equals to 4. At x equals to 4, the particle is achieving a stable equilibrium. And what is the at equilibrium? What is the value of potentiality? That potential is the minimum potentiality. What is minimum potentiality? Minimum value is basically 8x minus x square, and in that x put the value of 4. So 32 minus 16. Okay, that is 16. So 16 will be the minimum potentiality. That you also can calculate. Okay. Let us do another situation where u value is given as 12x minus x square. So again, first step is du dx equals to 0. Once I differentiate it, I am getting 12 minus 3x square. And if I put it equals 0, so x square becomes 4, so x becomes plus minus 2. Okay, so I have two value of it at which the equilibrium is possible. That means at these two locations, I have to check whether I am getting the stable equilibrium or unstable equilibrium. Now for the checking of that, I should go for the second derivative. So once I do the second derivative du dx square, this value comes to be as minus 6x, because 12 minus 3x square differentiation, so 12 becomes 0. So minus 3 square minus 6x. So now the minus 6, if I put x equals to plus 2 over there, so for that I am getting it is equals to minus 12, negative, that is stable equilibrium. So stable equilibrium at x equals to plus 2. If I put x equals to minus 2, then I am getting plus 12. Okay, so plus 12. So plus 12 number is greater than 0. That means it is unstable equilibrium. Okay, unstable equilibrium. So depending on whether I am getting the positive number or negative number, I have to comment whether I am getting the stable or unstable. Now, once I am getting two information of it, I have to check for both the points. So at plus 2 and minus 2, I have to both the point I have to check, and accordingly I can say whether I am getting the stable equilibrium or unstable equilibrium. Okay. So the potentiality of a system of two particles is given by this. So this is the potential function given. If you are asked to calculate the minimum value of potentiality of the system, that means since you are working on the minimum potentiality, that means the system is. Now I know that for minimum potentiality, the du dx is equal to, so du dx is what? So d dx of a by x square minus d dx of b by a, that number should be equal to 0. Okay, d dx of a by x square means minus x to the power minus 2 minus 2 by x cube x cube. So minus 2a by x cube, and it is x to the minus 1, so minus 2b by x square, but it becomes plus. So 2b by x square, that number is equal to 0. Okay, so 2 cancels out, so b by x square should be equal to a by x cube. Okay, so here there will be no 2. No, no 2. It's a minus 1, so there will be no 2. So 2a is there. 2a is there. Okay. So ultimately what I am getting, x number should be equal to 2a by b. Okay. So at 2a by b, the potential energy is minimum. Now we are asked to calculate what is the minimum value. So put the value of x equal to 2a by b in the potential energy equation. So what is the u number? U should be equal to a by x square. X means 2a by b whole square minus b by x means 2a by b. Okay. So give a into b square by 4a square minus b square by 2a. We give b square by 4a minus b square by 2a, that is minus b square by 4. That is the answer. Okay. So minus b square by 4 is the minimum of the potential. So in this situation, first of all, you have to differentiate it and get the answer for x. So this is the location for minimum. So at this location, I am getting the minimum value of potential energy, and once I put this location value in front of the U parameter, I am getting the minimum value of the U. So once I am getting minimum value, that means I can conclude that the potential is minimum, means the stability is stable. The stability equilibrium is achieved. Now potential energy of the particle of mass 5 kg moving in the xy plane is given by this thing. Okay. See, the particle starts from rest, from origin, then the speed of the particle at t equals to 2 seconds. So the particle is moving in the xy axis system. Particle moving in the xy axis system in such a way such that the potential energy is given as U equals to U value is given as minus 7x plus 24. This number. Okay. Minus 7x plus 24. So if the particle starts from rest, so initially the particle is at point A, let us say, this is the location of the particle at origin. So at origin, x equals to 0, y equals to also 0. So what is the potential energy at point A? So potential energy point A equals to 0, because if I put x equals to 0 over here, y equals to 0 over there, certainly potential energy equals to 0. Now the particle starts to move. So speed of the particle at t equals to 2 seconds. After 2 seconds, particle may be at any other location. So correspondingly, they were asked to calculate the speed at that position. At t equals to 2 seconds. So at t equals to 2 seconds, so let us say the speed is v. Corresponding to that, can I say the kinetic energy of that particle at 0.2 seconds is half mv square? If I say v is the speed at this particular situation, so correspondingly kinetic energy of the particle is equal to half m into v square, So v square means half into m is 5 and v square is there. So 5 v square by 2. That is the kinetic energy. And after t equals to 2 seconds. And after t equals to 2 seconds, initially another information is given that the particle starts from rest. Okay. Initially the particle is at rest. So initially the particle is at rest means what I can say, initially kinetic energy initially basically 0. Kinetic energy initially 0. Why the particle is at rest? Okay. So particle is moving, and because of that the kinetic energy is being changed from 0 to 5 v square by 2. Now what is the change in kinetic energy? Delta k. And for the change in kinetic energy, simplify v square by 2 minus 0. That is 5 v square by 2. 5 v square by 2. Now, because of this is a change in kinetic energy. Now, why this change in kinetic energy takes place? Because of the applied force. So, force must be there because Q is there. No? Q is there. So, that means the particle is displaced because of some kind of force. And because of that, the change is changing kinetic energy. Now, changing kinetic energy is nothing but the work. Changing kinetic energy is nothing but the work. Now, how to calculate the work done? So, U is there. So, conservative work. So, work done can also be written as delta W. But W is equals to minus of delta U. Work done by the conservative force equals to minus of delta U. Or, since the variation is given, so I can also calculate that equals to F equals to minus of du, or what is the force that is equals to minus of del u del x I minus of del u del y g. Can I write it? Yes. Okay. So what is del u del x? Del u del x is 7 minus 7. So ultimately I am getting 7i, and del u del y is what? 24. So with the minus say minus 24g. Once I do this, I understand that the force acting on the particle is constant. Because 7i minus 24, that number is constant. So under a constant force, the particle is now moving. What is the x component of the force? So x component of the force is 7 Newton. Y component of force is how much? Y component minus 24 Newton. So corresponding to that, what I can say, the acceleration along x direction, how much? Acceleration along x is equals to force by mass 7 by 5, and acceleration along y is equals to how much? Minus 24 by 5 meter per second square. Now it is also given that the kinetic energy, it is also given that initially the particle is at rest. So since the particle is moving, so in both the direction it has acceleration. So Vx should be how much? Ux plus ax into t, that is 0, plus t is 2 seconds. So 14 by 5 meter per second. Okay. Similarly, the velocity along y should be how much? Velocity along y should be uy plus ay into t. What is ay? Y minus 24 into 2 by 5 minus 48 by 5 meter per second. Okay, meter per second. So these are the two velocity component along x and y direction. So you are asked to calculate speed. What is the speed? Now what is speed? Speed is basically dx square plus vy square square. The speed of the particle would be equal to root of 14 by 5 whole square plus 48 by 5 whole square. Okay, meter per second. To calculate it, how much?